so find the roots of the denominator, and we only need the roots with the positive imaginary part. Okay, so now let's look at the integral. So hn is given by this, and hm, we change n to m. Okay, so you can see whenever you have n change to m, and star is the complex conjugate. Okay, so this term is changed to negative. Okay, then for both the numerator and the denominator, we multiply the complex conjugate. And you separate the real part and the imaginary part. Okay, so this is the real part, and this is the imaginary part. Okay, so the real part is given by this integral, and the imaginary part by the second integral. Okay, so now let's look at how to evaluate this integral. This is of the form in the method of residue. So both the numerator and the denominator are polynomials. We want to find the roots of denominator. Okay, so find the roots of the denominator. And you can see this term and this term are the same, except the subscript. We have m for the first term and n for the second term. Okay, so the roots will be similar. Okay, so now let's look at this term first. When you expand, it's a polynomial of degree 4. Okay, so we should have 4 roots. And you can regard this as a quadratic of omega squared. Okay, and then use the formula for quadratic equation, and we find the roots for omega squared. And then you take a square root through complex numbers and find the roots. Okay, so we have 4 roots. Two roots here and 2 roots here. Okay, so we only need the roots with positive imaginary part or parts. Okay, so we have this term, and this term. Okay, so if you combine this, we have, for the m term, we have 2 roots. And for the n term, we have another 2 roots. Okay, so total we have 4 roots out of 8 roots that are in the upper half plane, always positive imaginary parts. Okay, so once we have this, then we can evaluate the residue at the roots, okay, or in this case, they are called poles. Okay, now you can use any symbolic computational software. I mentioned that Maple was developed at the University of Waterloo, and then you have Mathematica, and you may use MathCAD. I was told that MathCAD has a portion of Maple. Okay, so let's say we use Maple, and if you don't have Maple, the language probably is the programming is very similar. Okay, so we will go through this. Okay, so when you integrate, we find that the integral from the imaginary part is 0. For the real part, it can be simplified to this expression. Therefore, the integral can be obtained like this. Okay, it's quite amazing that people were able to evaluate this complex integral in the 70s by hand. And if you use Maple, it's quite easy to evaluate. Okay, so we write the Q is the denominator of both integrals, and we express in terms of the poles or in terms of the roots. We have total 8 roots. Okay, and IP is the numerator, and then Fi is the integrand of the integral for the imaginary part, and Fr is the integrand for the real part. Okay, so just write the expressions, and we find the roots. Okay, the 8 roots, and this is just a test to show that the roots are actually the roots. The roots we find are correct. Okay, and then we use the theorem 8.1 or the theorem of residue to evaluate the integral. Okay, so we need RM1 Where's RRM1? Yeah, RRM1 is here. Okay, so it's the residue. That's a maple function. To evaluate the residue at the first root. Okay, and only root 1, 3 have positive real part, and roots 2 and 4 have negative real parts. Okay, so we evaluate the residue at the 4 roots and add them up, multiply by 2 pi I. And at the end, if you have a semicolon, that means show the result. And the column means does not show the because if you show the result, it will be very long. Okay, so at this point, there's no need to show the result. Okay, so we add them up. And usually when a function is in the form of a complex expression divided by another complex expression, it is difficult to simplify the function on its own. The numerator and the denominator of the function must be simplified separately. Okay, so for example, if you have x squared plus 2x plus 1 and say x4 plus 2x squared plus 1. Maple does not know how to simplify this. Okay, but if you simplify the numerator, and the denominator separately, then you have x plus 1 squared, and the bottom is x squared plus 1 squared. Okay, so the numerator and the denominator of the function must be simplified separately. Okay, so that means we extract the numerator. So get the numerator of this expression, and DNOM get the denominator of the expression. Okay, then you expand and factorize. I have it here. Okay, factorize means okay, and so you expand, simplify the numerator, simplify the denominator, and then divided them, and then you have a very nice simple expression. Okay, and then you can use this result here. That's obtained from Maple. Okay, but if you want to evaluate this by hand, it's very tedious. Okay, so we find the integral, and then the coefficient of correlation between the mth mode and the nth mode. For the special case, when m is equal to n, we have this integral, and that's the result. Okay, so that's a simple introduction of how to use Maple to evaluate a complex integral using the method of residue. Okay, another thing that's important, we will study this in more detail at the end when we look at seismic design, is when we have, okay, maybe go through this again. Okay, if you have, say this is the omega m, omega n, so that means omega m is not close to omega n. And in structural dynamics, we call the structure has well separated modes. Okay, so if omega m and omega n are not close, we have well separated modes. And in this case, rho mn is very small. Okay, so now if all modes are well separated, then we can use SR-SS combination. Okay, because rho mn is small for all combinations of modes. On the other hand, if this is omega m and this is omega n, then omega m is close to omega n, so that means we have closely spaced modes. And in this case, rho mn is large. Okay, so for example, close to 1. And so if a structure has closely spaced modes, we have to use CQC combination. Okay, so in general, you can always use CQC combination. And this is a general case. Only when all the modes are well separated, CQC is reduced to SRSS. Okay, so you can always use a CQC, just slightly more work to find row MN. But if you want to write a program, then it's easier to write a subroutine to find the row MN, then you always use CQC. Okay, so most of the time you use RSS only when you want to do it by hand, and then it's an approximation. Okay. Okay, so now it is very important to note that using the CQC or the SRSS combination rule must always be the last step in evaluating the maximum value of any response quantity. So, for example, if we have okay, so for example, let's say you use CQC to find the maximum base shear V CQC. Okay, now you cannot use this is the base shear of a building, and okay, so let's say is equal to no, I don't have a simple expression. I don't have a simple expression. So you can just say you cannot use VCQC to find M does not equal to H times V CQC, okay, or P times V CQC. That overturning moment. Okay, so this is not very accurate, but just want to show you the idea. This is wrong, okay? So we cannot use VCQC to find Lennard quantity. Okay, so what you have to do is you have to have M equal to AN QN, and then use this CQC to find M CQC. Okay, so that's the basic idea. You cannot use VCQC to find the overturning moment. You have to use modal response, and through CQC to find MCQC. Okay, so that's what it says. In other words, one cannot use the maximum value of one response quantity, for example, VCQC, obtained using CQC to evaluate the maximum value of Nénard response quantity, MCQC. Okay, so we have to go through, for each quantity, we have to go through CQC or SRSS to find the maximum value. Okay, so now we study a new topic on nonlinear systems. For nonlinear systems, in general, we have two very popular methods. One is the method of averaging. When we look at the dynamic stability, I introduced the method of averaging a bit. The method of averaging is also a general method that can be used to study stochastic or nonlinear stochastic system. Okay, because of the time constraint, we will not study the method of averaging. And today we will introduce the method of equivalent linearization. And equivalent means "等效线性化". Okay, so the method of equivalent linearization, which replaces a nonlinear system by an equivalent linear system, is useful in determining the mean square response to stationary excitation. And we have a table in the notes that lists the properties of Gaussian random variables. Okay, so you can take this as a given set of properties. X1, X2, Xn are Gaussian random variables with mean 0. Okay, so Gaussian mean 0, then the expected value of 3 variables is equal to 0. The expected value of product of 4 variables can be expanded like this. Okay, so what we do is you pick up 1 and 2. Okay, pick up 1 and 2, then you have 3 and 4 left. Then you pick up 1 and 3, then you have 2 and 4 left. You pick up 1 and 4, you have 2 and 3 left. So in general, if you have an odd number of terms, the expected value is 0. So for example, if you have 3 terms or 5 terms, then the expected value of the product is 0. Now here you have even number of terms, then it's a product of this. Okay, so where the summation involves 2m factorial over 2m, 2 to the power m, m factorial. that many terms and is to be taken over all different ways by which 2m elements can be grouped into m distinct pairs. Let's look at a simple case. You have 1, 2, 3, 4, 5, and 6. So you would have x1 and x2. Okay, so for first, and then you have 3, 4, 5 left. So that can go with 3, 4, and then 5 and 6. Then you go 3 and 5. Then you have 4 and 6. Then you can go 3 and 6, and then 4 and 5. Okay, then you would pick up 1 and 3. Then you have 2, 4, 5, 6. Okay, so you go 2, 4, 5, and 6. Then you have 2, 5, 2, 5. Then you have 4 and 6. Then you have 2, 6. And then 4 and 5. Okay, and so on. So quite a few terms involved. And normally we have 4 terms would be enough in our nonlinear system. Okay, we will see in a moment. But using this general formulation, you can derive the formula for the expected value of a product of many Gaussian random variables. Now, if x is a stationary process, then this is the definition of autocorrelation function. And the derivative of the autocorrelation function is the correlation function between x and x dot. And the double prime is the correlation function of x dot and x dot. Okay, with a negative sign. Okay, so we take these formulas as known or given. Okay, so now let's look at a simple example to introduce the method of equivalent linearization. Okay, so here we have a single degree of freedom system. So this is a second order differential equation. Okay, so here x dot is the velocity, so we have nonlinear damping. And gx means we have nonlinear stiffness. Okay, so we have a nonlinear system, and we want to replace this nonlinear system by the equivalent linear system. Okay, so x double dot plus beta x dot. I missed a dot in the notes. Please add a dot here. Okay, so that's the linear damping plus omega 0 squared x linear stiffness Okay, so the first equation is nonlinear, and we want to replace it by the equivalent linear system. Okay, the error of linearization means the error in replacing the nonlinear system by the equivalent linear system is given by this. Okay, so the difference between the stiffness term. Okay, so that's the linear stiffness. This is the nonlinear stiffness. And the error in the damping term, this is the linear damping. And this is the nonlinear damping. Okay. And because Ft usually is a random process, since we are studying random vibration. Okay, so the error epsilon is also a random process. Okay, so this quantity epsilon is a random process. Now, if the error is zero, so that means there's no difference between the equivalent linear system and the original nonlinear system. Then we can use the equivalent linear system to find the response. Okay, so use what we studied in the previous section. We can find the mean square response of the linear system. Okay, so SFF is the power spectral density function of the excitation. Okay, and the denominator is the frequency response function. Okay, so we can evaluate this. Now, since we don't know beta and omega 0, okay, so we want to find the parameters beta and omega 0. They are chosen in such a way that some average function of the error epsilon is minimized. Okay, so epsilon is an error. It's the error. It's a random process. So we want to have some average function of the error be minimum. Okay, so for simplicity, replace omega 0 squared by alpha. Okay, alpha is omega 0 squared. So first we call this epsilon 1 and call this epsilon 2. So epsilon 1 is the error in the stiffness, and epsilon 2 is the error in the damping. Okay, so you can select any function, average function of error to minimize. The usual choice is to minimize the mean square error. Okay, the usual choice. You can have other choices, but it's convenient to minimize the mean square errors. Okay, so the expected value of epsilon1 squared expand, mean square value of epsilon2 expand this, and since we want to minimize these two functions with respect to alpha and beta. Okay, we want to minimize the function with respect to alpha and beta. So for the first term, we differentiate with respect to alpha. And you can find alpha is given by this. And the second term is the error in the damping. So we differentiate with respect to beta because we have a beta square here and alpha. So we have beta and then you find beta. Okay, so equation 3.44, the mean square response, and these two equations, alpha and beta, are solved to determine the mean square response. And two parameters, alpha and beta. Okay, so now it's 8:48. We take a 10 minutes break, and then we will come back and look at an example. Okay, so please come back at 8:58. 10 minutes break. Okay, thank you. Let's continue. We have a single degree of freedom nonlinear system with nonlinear damping. Okay, after I send you the notes, I find we can make the presentation much better. Okay, so if you have the notes, please work with me and then we change some of the notation. Okay, so let's call this beta 0. Okay, so here we have nonlinear damping. And linear stiffness. Okay, so the excitation Ft is a white noise process with power spectral density equal to S0. Okay, so first we replace the equation, the nonlinear equation, by an equivalent linear system. Okay, so you have x double dot plus beta x plus omega 0 squared, beta x dot plus omega 0 squared x equal to Ft. So this is the equivalent linear system. Okay, so what we have here is the nonlinear system, the nonlinear term is replaced by the equivalent linear term. Okay, so once we have the linear system, we can use what we studied in the previous section to find the response. Okay, so the Sxx now we say this is the response of the equivalent linear system. So Sxx is the frequency response function squared times the power spectral density of the input. The power spectral density of the input is S0. Okay, so we have this, and that's the frequency response function. And if we take the inverse Fourier transform, the autocorrelation function is given by the inverse Fourier transform of the power spectral density function. Okay, so plug this term in. And you integrate, you can get the response. Okay, so now if we set tau equal to 0, we get the mean square response. Okay, so that's Rxx at 0, we get the mean square response. So replace tau by 0. Okay, so we end up with when tau is 0, this is 0, and the cosine is 1, and E is 1. So we only have this term left. Okay, so that's the mean square response. And from here, substituting here, we find this integral is this. Okay, so if you have a maple, you can use a maple to do the integral. If not, then you have to do it by hand and find the integral. Okay, and actually you can use what we have before. Okay, you can take this integral as a formula from the notes in the previous section. Okay, so the mean square response is given by this. If you differentiate the autocorrelation function, we get the first order derivative and second order derivative. And the first order derivative is x and x dot. Second order derivative is x dot and x dot negative. Okay, so we can get this quite easily. Okay, now from this equation, this is the mean square value of velocity. Okay, so that's the mean square value of velocity. And it's omega 0 squared sigma x squared. And sigma x squared is S0 over 2 beta omega 0 squared. Okay, so we find the mean square value of the velocity. This is the mean square value of the displacement, mean square value of the velocity. Okay, so now the error is beta x dot. This is the equivalent linear term, and this is the nonlinear term. Okay, the nonlinear term has a beta 0. It's different beta. Okay, so please add a 0 for this beta. Okay, so we want to replace this nonlinear term by the equivalent linear term. And since we only have one variable, therefore we have only one error. Okay, so we want to minimize the mean square error, epsilon 2 squared. Okay, so you want to find the mean square value. Okay, so now we have x dot fx dot okay 3.47. Okay, from equation 3.47, it's this equation. Okay, so we need beta, expected value of x dot and fx dot divided by the mean square value of x dot. Okay, maybe I copied here. Beta is E x dot f x dot over E x dot squared. Okay, so this term is equal to beta expected value of x dot squared. And the expected value of x squared, we find it here. Okay, so this term is S0 over 2 beta. So you find that. Okay, so now evaluate this term, x dot, and then f, we have beta 0 here. Okay, so add a 0 for this term. When you expand, you have beta 0, expected value of x dot, epsilon, and x dot to the 4. Okay, this term we already have. This term we already have. It's the mean square value of velocity. Okay, so now we want to evaluate this term, x dot to the power 4. Okay, so you go back to this property. We want to evaluate x dot to the power 4. So basically we have x1 is the same as x2, x3, and x4, it is x to the dot. Okay, so compare these two. Okay, so you would have, this is x dot squared, x dot squared, x dot squared, and x dot squared, x dot squared, x dot squared. Okay, so that gives us 3 e x dot squared. Okay, so now you can see why this formula is useful. Okay, so if you have a cubic nonlinearity, you would have x dot to the power 4. If you have a nonlinearity of power 5, then you have x dot to the 6. Okay, so remember this term. Okay, so that's 3 ex dot squared to the square. Okay, so each term we have. Each of these we have. Okay, so you substitute the mean square value from here. Ex dot squared is omega 0 squared sigma x squared. Okay, so omega 0 squared sigma x squared for each of the yellow term. Okay, then we have this. Okay, so now S0 over 2 from this equation, S0 over 2 is beta times omega 0 squared sigma x squared. Okay, so replace S0 over 2, it's beta omega 0 squared sigma x squared. And then we can solve for beta. Okay, so solve for beta. Then beta is equal to beta 0, 1 plus epsilon times 3 omega 0 squared sigma x squared. Okay. So from this equation, we find that okay, from here, sigma x squared is S0 over 2 beta omega 0 squared. Okay, and this is S0 over 2 beta zero one plus epsilon 3 omega 0 squared sigma x squared times not enough room times omega 0 squared. Okay, so That's this equation, except we have beta 0 here. Okay, and then beta 0 here. So this term we use Taylor expansion. Use a series. So 1 plus x is 1 minus x plus x squared minus x cubic, and so on. Okay, so that's for x small. Okay, so that's a Taylor series. So you have this block. It's 1 plus this block, so it becomes 1 minus this block. Okay, so now you replace this sigma x squared, or omega 0 squared sigma x squared from here. Okay, we need to change all this to beta. Beta is equivalent. Okay, so this term, omega 0 squared sigma x squared is, oh, it's here. Okay, use this term. Okay, so this term is replaced by this beta 0. And okay, so that's beta. And then you have probably do a expansion, or you say this beta is approximately beta 0, keeping only the first term, because when you expand, you have epsilon here, it's a higher order term. So if you use only the first term, that's what you have. Okay, so basically, you can replace this by beta 0. Okay, so sorry about all these changes. And the idea is the original equation is in terms of beta 0, and equivalent linear damping is beta. Okay, so it's better to distinguish these two terms. Okay, so you know one is the original beta 0, and the beta is the equivalent term. So after we go through all this, we find a relationship between beta and beta 0. Okay, and beta, the new term, is given by this. Okay, and then you express the mean square value in terms of the original system parameters. Okay, S0 is the power spectral density of the white noise, and beta 0 is the original damping coefficient. Okay, so just be careful when you perform the analysis. because we are dealing with a small parameter epsilon. Okay, so that's why in the original equation we always have small nonlinearity. Okay, always with a small term in the nonlinear terms. Okay, with always use a more parameter epsilon so that you can you know the order of the terms. Okay, so sorry about the changes, and it's better that you can go through this example after lecture. Make sure you are clear about the relationships between the parameters beta 0 and beta. Okay, and you have assignment number 4. One of the questions is using the equivalent nonlinearization to solve a nonlinear equation, okay, to determine the mean square response. And you can practice that. Okay, so that's all on the random vibration. Now we go into applications of random vibration in earthquake engineering. Okay, the next chapter is on seismicity. Okay, I have the notes, but it's too long, so I will use a slideshow to show you the basics of seismicity. Right, a second, I'll get a mouse. Okay, so in this part, we will look at the geological structure of the Earth and earthquake, and the tectonic theory and earthquakes, and the propagation of seismic waves, generation of tsunami, and finally we will look at the case study, and it's the 2011 Great East Japan earthquake. Okay, this is the internal structure of the Earth. The Earth has a layered structure. It has a very thin crust of about 5 to 80 kilometers. This blue shell is the crust, And then we have mantle. It has the upper mantle and lower mantle. The upper mantle is the this burgundy layer. It has about 670 kilometers. And the lower mantle is the orange part, 2230 kilometers. And then we have the core. It has the outer core and about 2250 kilometers. And then the inner core, the radius is 1220 kilometers. Okay, so the outer core has a temperature of 4700 degrees centigrade. So it's very hot in the core of the Earth. Okay, the theory of earthquake is based on the theory of plate tectonics. 中文是板块理论。Plate tectonics is one of the foundations of modern geology. 250 million years ago, there was a supercontinent called Pangaea. Okay, so in 250 million years ago, the Earth is one big plate, and this big plate or a supercontinent, 超级大陆, is called Pangaea. And then Pangaea broke apart in the continents about 200 million years ago. Okay, so the supercontinent broke apart. And this is a simulation 200 million years ago, and you can see the big continent broke up, and then 170 million years ago, 150 million years ago, 120 million years ago, and 105, 90, 65, 50, 35, 20, 50,000 years ago, and the present world. Okay, so, and all these continents all came from a supercontinent, Pangaea. Okay, so now let's look at the motion of the continent. We know that the top part, the blue part, is the crust. Okay, and then below we have the mantle. The upper portion of the mantle, this part, is in contact with the cool crust. Okay, the outer part of the Earth is cool, and the lower part of the mantle is in contact with the hot outer core. Okay, you can see here the outer part is the crust, and that's the mantle. The mantle is in contact with the cool crust and the inner part of the outer core. Okay, so there's a temperature difference or temperature gradient from the crust to the outer core. So the denser, cooler material resting on top of the less denser or warmer material. When the material becomes warmer, it becomes less dense. Eventually, the cool material, the cooler, denser material begins to sink under the action of gravity. Okay, if it's cool, it's dense, then it will sink. The sinking material gradually warms up and becomes less dense, Eventually, it will move up. Okay, so when it's cold, it moves down. And then when it moves down, it becomes warmer. And then when it becomes warmer, it becomes less dense, it moves up. Okay, so that becomes a convection process. Convection currents in the semi-molten 半融化 rock 半融化状态 rock of the mantle impose shear stress on the bottom of the plate. Okay, because the material goes up and comes down and goes up. It's like a boiling water. Okay, so the cold water comes to the bottom, it becomes hot, and then it rises up, and then the cold one comes down. So this is the convection process. Okay, because of this, it drags the crust in various directions across the surface of the Earth. Okay, because of this convection, the crust on top will move in different directions due to these forces. Okay, depending on the direction in which the plates move, we have convergent boundaries. So that means the two plates are moving towards each other. Okay, so it means convergent, where they tend to come together. This case. And when they tend to separate, we have the divergent boundary. Okay, so for example, in this case, the two plates move away from each other. And the transform fault when slide horizontally past each other. Okay, so if one moves fast, the other moves slower, then we have the transform boundary. Okay, so for example, this part moves faster, this part moves slower. And theory of earthquake is based on the elastic rebound theory. Relative movement of the plates causes stresses to build up on their boundaries. As relative movement occurs, elastic string energy accumulates in the vicinity of the boundaries. Okay, so for example, the light blue part moves in this direction, and the yellow part moves in the opposite direction. Okay, so then we have the locked fault. Okay, when a relative movement occurs, elastic string accumulates in the vicinity of the boundary. So we have elastic string energy builds up along the boundary. When the shear stress reaches the shear strength of the rock along the fault, the rock fails and the accumulated string energy is released. Okay, so that the effects of failure depend on the nature of the rock along the fault. If the rock is weak and ductile, string energy stored will be released relatively slowly. Okay, if the rocks are weak, then it will break constantly. And the string energy will be released relatively slowly, and the movement will occur seismically. Okay, so not seismically. Now, if the rock is strong and brittle, the failure will be rapid. Rupture of the rock will release the stored energy explosively, producing earthquake. Okay, so we have string energy build up. If the rock is strong, we need a large string energy to fail the rock. Okay, so when the rocks fail, the energy will be released explosively, producing earthquake. The size of an earthquake depends on the amount of energy released. So it depends on how strong is the rock along the boundary. Okay, according to the elastic rebound theory, different types of boundaries have different earthquake capacities. So if we have two plates coming together towards each other, we have the so-called subduction zone or convergent boundary. Subduction zone boundaries can produce the largest earthquakes. Okay, so one plate comes towards the other and it ducks and then goes underneath another plate. And the transform fault boundaries produce smaller earthquakes, and spreading ridge boundaries, when they move away from each other, very, very small earthquakes or no earthquake. Okay, so we don't have build up of string energy. So we are focused on the subduction zone boundaries. And fault is the break in Earth's crust along which displacement of rock occurs. So this is a photo of a fault. At a particular location, a fault is assumed to be planar with an orientation described by strike and dip. Okay, so we have this part and this part, and there's a fault between them. Okay, a fault is modeled as a plane. It has a dip is this angle, or the another direction is relative to the north. Okay, so that's the strike gives us this direction, and the dip is this slope. Okay, so strike is the compass direction relative to the north, this angle. Dip, the angle of inclination or slope relative to the horizontal plane. Okay, this angle. Focus is the point on the fault plane where an earthquake originates. Okay, so on the fault plane we have the focus, and the epicenter is the point on the Earth's surface located directly above the focus of an earthquake. So right above the focus on the surface of the Earth, we have the epicenter. And these two parts can move relative to each other. We have the dip slip movement, fault movement occurring primarily in the direction of the dip along the slope or perpendicular to the strike. Okay, so the normal faults occur when the ground is stretched and when the hanging wall moves downward relative to the foot wall. Okay, the portion on top is called hanging wall, and the part underneath is the foot wall. Okay, so here normal faults is the hanging wall slides downward or the foot wall moves upward. Okay, the reverse faults occur when the ground is compressed and when the hanging wall moves upward relative to the foot wall. And the strike-slip movement, fault movement occurring parallel to the strike, so in the horizontal direction. Right lateral strike-slip fault occurs when the observer would observe the material on the other side of the fault moving to the right. So if you stand here, this part moves towards the right relative to you. Okay, so that's the right lateral strike-slip fault. And if you stand here, this part moves towards the left. So we have a left lateral strike-slip fault. Okay, in general, we have movement in both the strike-slip and dip-slip directions. So in most cases, fault-slip is a combination of strike-slip and dip-slip, and it's called oblique fault. Okay, so we have movement in both this direction and this direction. Okay, so if you look at this direction, the hanging wall moves downward, so that's the normal fault. If you stand here, this part moves towards the left, so we have the left lateral movement. So this fault is called left lateral normal fault. Okay, so now because we have the movements, relative movements between the two plates, we have interplate earthquakes. Earthquakes occurring at convergent plate boundaries contribute more than 90% of the world's release of seismic energy. Most of the largest earthquakes have originated in the subduction regions as a result of the thrusting of one plate under another. About 10% of the world's earthquakes occur along the divergent ocean ridge system and contribute only about 5% of the world's total seismic energy. Okay, so 90% of the earthquakes occur at a convergent plate boundary. This is between plates. We also have intraplate earthquakes. Shallow focus earthquakes also take place within plates or intraplate, which cannot be explained by the plate tectonic theory. 不能用板壳理论来解释 in an obvious way. Intraplate earthquakes must arise from more localized systems of forces in the crust, perhaps associated with ancient geological structural complexity or with anomalies in temperature and strength of the lithosphere. Okay, so we all know this is the famous Ring of Fire. The Pacific Taipingyang Ring of Fire is an area where large numbers of earthquakes and volcanic eruptions occur in the basin of the Pacific Ocean. This is a Pacific Ocean, 太平洋. in a 40,000 kilometer horseshoe shape 马蹄状. It is associated with a nearly continuous series of oceanic trenches, 海沟 volcanic arc, and volcanic 火山 belt and plate movements. Okay, along the Ring of Fire, it has 450 volcanoes, over 75% of the world's active and dormant volcanoes. Okay, so this figure shows the 90% of world's earthquakes and 80% of world's largest earthquakes occur along the Ring of Fire. Okay, so this is the Ring of Fire. And I will show you a simulation. Okay, so it shows the eruption of volcanoes and earthquakes. Okay, so you can see here it's China, and that's US. This is Canada. So North America, China here, and Australia. Okay, and South America. So this is the Ring of Fire. Okay, so you can show the curve. You can see the curve of earthquake. The big dots are the big earthquakes. Okay, and then you can see here it's the date. Okay, I think you get the idea. Okay, so we know that most of the earthquakes occur along the Ring of Fire. Now let's look at the propagation of seismic waves. When an earthquake occurs, different types of seismic waves are produced. And there are two types of waves, body waves and surface waves. Body waves can travel through the interior of the Earth, and we have P waves and S waves. And another category of waves is surface wave. Surface waves result from the interaction between body waves and the surface and the superficial layers of the Earth. And we have Rayleigh waves and Love waves. Okay, so body waves travel through the body of the Earth, and the surface waves travel along the surfaces. Okay, now let's look at each waves in detail. P waves also called primary waves. So P comes from primary or compressional or longitudinal waves. They involve successive compression and dilation of materials through which they pass. Okay, so compression and dilation, compression and dilation. They are analogous to sound waves. The motion of an individual particle is parallel to the direction of the P wave. Okay, this is the direction of propagation of the wave, and the particle will move in the same direction. Okay, compression, dilation, compression, dilation. Like sound waves, P waves can travel through any type of material. The speed of body waves varies with the stiffness of the materials they travel through. Since geological materials are stiffest in compression, P waves travel faster than other seismic waves, at nearly twice the speed of S waves, and are therefore the first to arrive at a particular site. Okay, so remember, P wave travels the fastest, and its speed is about twice of the S waves. Okay, so it propagates with compression and dilation, compression and dilation. So if you look at a piece of frost, this is the direction of the wave, and you can see we have compression in this portion and the dilation in this portion, and then compression and dilation travels along the waves. Okay, S waves, also called secondary wave or shear wave. So S comes from secondary or shear or transverse waves. They cause shearing deformation as they travel through a material. The motion of an individual particle is perpendicular to the direction of S wave. The direction of particle movement divides S wave into two components, SV, shear vertical, or SH, shear horizontal. Okay, so if you look at the bottom diagram, this is the direction of wave propagation. So the particle moves up and down in the shear deformation. Okay, so this is shear vertical, up and down. And then if it moves in this direction, it's shear horizontal. S waves are slower than P waves with speeds typically around 60% of that of P waves in any given material. As wave shakes the ground surface vertically and horizontally, which is particularly damaging to structures, okay, because it goes up and down or in the horizontal direction left to right. As wave shakes the ground surface vertically and horizontally, which is particularly damaging to structures. Fluids which have no shear stiffness cannot sustain S waves. Okay, so this direction, shear wave travels in this direction. If the particle moves up and down, it's shear vertical. If it moves in the horizontal direction, it's shear horizontal. Okay, so you can see the deformation of a piece of the crust. Surface waves. Surface waves result from the interaction between body waves and the surface and the superficial layers of the Earth. They travel along the Earth's surface with amplitudes that decrease roughly exponentially with depth. Okay, so we only find surface wave on the surface of the Earth, and they decay exponentially with depth. Due to the nature of the interactions required to produce them, surface waves are more prominent at distances further from the source of the earthquake. At distances greater than about twice the thickness of the Earth's crust, surface waves rather than body waves will produce peak ground motions. Now we have two types of surface waves. Rayleigh waves. Rayleigh waves is produced by the interaction of P waves and shear vertical waves with the Earth's surface. They involve both vertical and horizontal particle motion. Rayleigh waves are also called ground rolls, similar to water waves produced by a rock thrown into a pond. Okay, so you throw a rock in a pond, then you have circles and the waves are going outside. Okay, they are slower than body waves, roughly 90% of the velocity of S waves for typical homogeneous elastic motion. Okay, so if this is the direction of wave propagation, a particle will rotate. Okay, so that's so-called ground rolls. And at the top, you have large motion and amplitude decreases exponentially with the depth. Okay, so when you see this, it looks like the ground is rolling. Okay, so that's a diagram showing the deformation of a piece of ground. Okay, that's the direction of wave propagation, and the particle moves in circles. And last, we have Laff waves. Laff waves result from the interaction of shear horizontal waves with a soft superficial layer. They have no vertical component of particle motion, okay? So only in the horizontal direction. They usually travel slightly faster than Rayleigh waves, about 90% of the S-wave velocity, and have the largest amplitude. The horizontal shaking of Laff waves is particularly damaging to the foundations of structures. And because liquid does not have shear strength, Laff waves do not propagate through liquids, only solids. Okay, so here if this is the direction of wave propagation, the particle moves in the horizontal direction, and the amplitude decreases with the depth. Okay, and this figure shows the displacement of the ground. Okay, now I will show you a simulation. Okay, that's the primary wave. You can see compression and dilation. This is a shear vertical wave. The particle moves up and down. The Rayleigh wave, and you can see the rolling of the surface. And the Laff wave. Okay, so you can see the particle moves in the horizontal direction. Okay, maybe watch one more time. Okay, I think I will not take a break. We will finish at around 10:30, okay? Okay, as the different types of seismic waves travel through the Earth, they are refracted and reflected. Refracted means 折射, reflected 反射. At boundaries between different layers as light beams. Okay, similar to light beams. If you have a light beam comes down, we have a mirror here, so it's reflected. And there's water here, air on top.
季老师
啊，
我这边好像看不到您的那个屏幕哎，我不知道那边学生们能不能看得到。
哦，看不到啊。
对，这边显示教授 post the screen share， 我不知道那边学生能不能看得到。
哦，行，我再看一下。
哎，
看不看得见了？
可以看到了，教授。
All right。
哎，现在可以看到了。
Okay, maybe I repeat this. As light, as different types of seismic waves travel through the Earth, they are refracted, and refracted means 折射, reflected 反射 at boundaries between different layers as light beams. Okay, so we look at this. You have a container, a bottle, and we have water at the bottom and air on top. So we have a light beam coming down. There's a mirror here. Okay, so that's reflection, reflect. And then at this boundary, you have reflection. And then another beam coming down, reflect. And here the refract, 折射, 反射. Okay, when a wave is reflected or refracted, some of the energy is converted to waves of the other type. Okay, seismic waves reach different points on the Earth's surface by different paths. In strong ground shaking on land, after first few shakes, a combination of the two kinds of waves is usually felt. Okay, so let's look at this. And we have the focus here. And so earthquake occurs here. Okay, so along the surface, we have surface waves. And then in the body, we have body waves. Okay, so if you look at this, you have body waves, and to the surface, it reflects to this. Okay, and then if you follow this, and to here, it reflects to this, and it refracts to this light blue part. Okay, then to this interface, you have refraction here and reflection here. Okay, so now this is a more complex diagram on the right. So P means P waves, and S is the S wave, and C, look at the C, is the wave reflected at the outer core of the surface. Okay, so we have C here, and you come here and then reflect and refract. Okay, so basically we have different types of waves. And when the waves go through the different interfaces, through refraction and reflection, and they interact with each other to produce different seismic waves. Okay, so now this shows the earthquake occurred in Haiti on Tuesday, January the 12th, 2010, and it's recorded in Manitoba, Canada. Okay, so that's a long way from Haiti, to Manitoba in Canada, 加拿大. Okay, this is in the east-west direction. You can see the P waves travels the fastest, and then followed by S wave, and the lava wave in the north-south direction. These are the two horizontal directions, east-west and north-south. And that's the vertical direction. Okay, and then we have this portion is the Rayleigh wave. Okay, so you can see we have different types of waves. Okay, now I'll show you a simulation. Okay, so we select earthquake, and we look at the 2011 Tohoku earthquake in Japan. It occurred on March 11th, 2011. Okay, we select this. Okay, so the earthquake occurs, then you see the wave propagation. And then on top, it's the record at different stations. Okay, so you can see the P waves goes first, and then you can see the different refractions and reflections in the Earth. Okay, we look at once more. Just this shows the waves propagating on the surface of the Earth. And then this diagram shows the reflection and the refraction of different waves at different interfaces or boundaries. Okay, this diagram on top shows the ground motions recorded at different stations. Okay, now let's look at the generation of tsunami. Okay, so here we have two plates, and this is the top plate, this is the bottom plate, okay? And we have the convergent or subduction. So this plate goes underneath the top plate. As relative movement of the tectonic plates occurs, tremendous elastic strain energy is built up in the material near the boundary. So we have the two plates are stuck together at this boundary. When the shear stress reaches the shear strength of the rock along the fault, this part, the rock fails and accumulated strain energy is released. Okay, so when it's released, this like a slingshot, 弹弓, it springs up. Okay, so this springs up. So originally it's in this shape, then it springs up and bring this body of water up. The sudden displacement in the seabed is sufficient to cause the sudden raising or lowering of a large body of water. Okay, so it kicks this body of water up, and then the water will propagate. Okay, so take a look at this diagram again. Before the earthquake, we have a lock between the two plates. When the strain energy or the shear stress reaches the shear strength of the rock here, the rocks fail and the strain energy is released. This piece will suddenly spring upward and kick the water up, and then the water will propagate. Following the initial disturbance to the sea surface, waves spread in all directions. Their speed of travel in deep water is given by square root of g times h, where h is the sea depth and g is the acceleration of gravity. Okay, so you can see here, this part moves up, so kicks or pushes this part of the water up, and then the water will spread in all directions. In the open sea, tsunami waves are characterized by very large wavelengths, reaching tens to hundreds of kilometers. Their velocity, depending on the water depth, can reach values as high as 800 to 900 kilometers per hour, because the depth is very deep. Okay, they can propagate for thousands of kilometers without dissipating much of their energy and can travel long distances at a very high speed, 800 to 900 kilometers per hour. And tsunami waves are usually unnoticed because of their height commonly not exceeding 1 meter. Okay, so the wavelength is very large and the height is very shallow. Now when tsunami wave approaches the coast, their velocity decreases directly proportional to the water depth because it becomes shallow and shallower. Okay, h is smaller, therefore the velocity is smaller. Their height increases and can reach tens of meters. Okay, so you can see this. And depth, velocity, and wavelength. If the depth is 7,000 meters, velocity is very high, wavelength is very large. And close to the shore land, depth is 10 meters. Velocity is much slower, 36 kilometers per hour. The wavelength is also much shorter. Okay, but the height is very high now. And you can imagine this. You have a lot of cars traveling on a highway with very high velocity, very high speed. Okay, then suddenly the cars slow down, so you have all the cars pile up. Okay, so you have a big accident. And this diagram shows clearly. Okay, size of earthquakes, and oldest measure of earthquake size is the earthquake intensity. The intensity is quantitative, is a qualitative description of the effects of the earthquake at a particular location, as evidenced by observed damage and human reactions. Okay, so the oldest measure is the modified Mercalli intensity, MMI scale. So level 1, not felt, nothing. And then when you increase to level 12, total damage, waves seen on ground, objects thrown into air. Okay, so with level increases, you have different behavior of human awareness and damage to the buildings. Seismic instruments allow an objective, quantitative measurement of earthquake size in terms of earthquake magnitude. Most magnitude scales are based on measured ground motion characteristics. For example, we have the Richter scale, local magnitude, ML. It is base 10 logarithm of the maximum amplitude of waves recorded by seismographs, adjusted to compensate for the variation in the distance between the various seismographs and the epicenter of the earthquake. Okay, so if you have an earthquake record like this, the maximum amplitude is A, then you can calculate the Richter local magnitude using this formula. And the log base 10A, and A0 is an empirical function, depends on the epicentral distance, delta of the station. And we have other magnitude scales. For example, surface wave magnitudes, magnitude MS, is based on the amplitude of the Rayleigh waves. Body wave magnitude MB, based on the amplitude of T waves, which is not affected by the focal depth of the source. Because these amplitudes tend to reach limiting values, these magnitude scales may not accurately reflect the size of very large earthquakes. Okay, so shows this diagram. We have local magnitude ML, surface wave magnitude MS, short period body waves, wave magnitude MB, small MB, and long period body wave magnitude MB, this black, and Japanese Meteorological Agency magnitude MJMA, this dashed red line. So you can see when the earthquake is large, they tend to saturate. Okay, they cannot reflect the true magnitude. So because these amplitudes tend to reach limiting values, these magnitude scales may not accurately reflect the size of very large earthquakes. The moment magnitude, which is not obtained from ground motion characteristics, is able to describe the size of any earthquake. Okay, so we have the moment magnitude. For strong earthquakes, the measured ground shaking characteristic become less sensitive to the size of the earthquake than for smaller earthquakes. So we use this. The only magnitude scale not subject to saturation is the moment magnitude, given by this formula, MW. In here, MO is the seismic moment. It's given by mu A d bar. Mu is the rupture strength of the material along the fault. A is the rupture area, and d bar is the average amount of slip. Okay, this formula, the seismic moment is a measure of the work done by the earthquake. And so you can see the solid black line is the moment magnitude. Other magnitudes would saturate for large amplitude, large size earthquakes. Earthquake magnitude scales are logarithmic. A unit change in magnitude corresponds to tenfold change in the magnitude parameter. The total seismic energy released during an earthquake is often estimated using this formula. So a unit change in magnitude corresponds to 10 to the power 1.5 or 32-fold change in energy released by earthquake. So for example, the energy released in an atomic bomb of the size used at Hiroshima is 19,000 ton TNT equivalent. And so you can see ML for scale 6 earthquake, it's equivalent to 0.8 nuclear bombs. 7, 25 nuclear bombs. 8, 794 nuclear bombs. And 9, 25,000 nuclear bombs. Okay, so I will stop here for today, and we will continue next week. That's all for today. Thank you.
教授，
谢谢。